Hello guys, now we'll be discussing about some key concept related to Jahn Teller effect. So first of all, we need to remember the system must have uneven filling of electrons and due to which there is some distortion in the geometry, ultimately giving rise to some stability in the system. Now let's discuss how all these are taking place in the system. For this we need to understand during the complex formation the d orbital set splits into two subsets of orbitals, namely Eg and T2g. Right, so here three orbitals are dxy, dyz and dzx, and this one is dx square minus y square and dz square. Whenever there is not symmetrical electrons in these three orbitals or these two, then there will be some distortion in the overall structure. In octahedral complexes, we know the ligands binds to the metal along the x-axis and y-axis and z-axis, so therefore the asymmetrical filling of Ez orbitals will have higher Jahn Teller effect than this T2g set. Like if we have T2g3 Eg1 or T2g6 Eg3, this kind of electronic configurations give rise to strong Jahn Teller distortion. Let us further explore it. If you see the geometry of octahedral complex, if it is the z-axis, this one let us call y and this one is x. Now if there is more electron in the dx square y square than dz square, then ligands approaching along this axis will be repelled more than the z axis and vice versa. If the electronic configuration is dx square y square 2 dz square 1, then ligands coming along the x and y axis will be repelled more than the two axial ligands. So hence the overall geometry will be slightly distorted in manner, like the z bond length along the z axis will be slightly lower than the bond length along x and y axis. So this case we are terming as Z in, since the bond length along the z axis is lower than the x and y axis. Similarly, if the electron configuration is dx square y square is having 1 and dz square having 2, here the ligands coming along the z axis will be repelled more than the x and y axis. So therefore in this case there will be some elongation of bonds along the z axis, and here we term with this distortion we term it as z out. If we consider the example of the complex copper is 2 whole 6 2 plus, here copper has 9 d electrons, it is a d9 system, and the electron filling will be like this one: 1 2 3 4 5 6 7 8 and 9. So there is one unpaired electron in the EG subset of orbitals. So if there is there is more electron in dx square y square, then the bonds along the z axis should be lower in length comparison to bond length along the x axis and y axis. But experimentally we have found that in most of the cases, in copper complexes, we found that there are 4 shorter bonds and 2 longer bonds, which implies that the EG subset is subset configuration will be tx square y square 1, tz square will have 2 electrons, because as dz orbital have 2 electrons, more electrons than tx square y square, so the ligands coming along the z axis will be repelled more, and thus their bond length will be more than the bonds along the x and y axis. This distortion further splits the energy levels of this orbital set in such as the T2G will be having 2 energy levels. This is dxy, dxz and dyz, and the T2G will be like this one: dx square y square and dz square. So ultimately the overall stability will be more than the non-distorted or the perfect geometrical shaped complex. This is due to as in this configuration you can see that the highest energy level orbitals is not completely filled, so that is why we will gain some stabilization energy through this distortion. Again, if we consider some other examples, like in T1 titanium X aqua complex, which is a D1 system, so the energy levels of the orbitals are dxy, dyz, dzx and dx square y square dz square. Here, since there is only one electron. So ultimately, again we found that the T2G level there is asymmetrical filling of electrons. Again, this will be again getting splitted into subset. So dxy will be having the lowest energy level, followed by dx yz dzx, and also the Eg level will be splitted like this. Again, since the electron is in the xy plane, so the bond length along the axial bonds, which are along the z axis, will be shorter than the equatorial bonds. So here we will see Z in effect, and where axial bond length will be shorter than the equatorial one. Due to the split of these energy levels, we will see two different spectrum of, two different peaks of at the UV spectra, while the electron get transferred from T2G to Eg levels, because there are two way of transition. So we will be getting, otherwise in ideal scenario we will be getting only one peak, but due to the split of these levels, the energy level of xy and x square, y square and z square, will be getting two signals. So in summary, we need to remember a couple of things, like if there is uneven or asymmetrical filling of electrons, and also we need to remember that we will find strong distortion when Eg orbitals are asymmetrically filled. As I told you, Eg orbitals, the position of these orbitals are directly along the axis of ligands, so the impact will be higher. So basically that's all for Jahn Teller distortion. Thank you for watching.